You could capture work pressure effects. You could track representation. And generally, you could examine how interventions or innovations at the level of the service process in the facility rippled through to interventions, to population health gains. So that's one type of hybrid model. A second type of hybrid model we saw yesterday involved agents whose dynamics were governed by stock and flows. So yesterday we saw a situation where we had a person whose weight was characterized, and regulatory processes were characterized by system dynamics modeling. Remember that? The stocks and flows, they had weight dynamics. And those were shaped by the environment around them. We today have just been looking at an example where, again, agents are being driven by system dynamics within each agent. Yesterday, that was accompanied by state charts. Here, it was more or less the only dynamics associated with homes and with workplaces, other than people coming and leaving, was governed by this by the stock and flow equation, right? Now, I'd like to show you a very different type of combination of system dynamics and agent-based modeling, okay? And actually, my hope is to show you two examples before the day is out. Two examples, both of which I believe could have relevance, potentially strong relevance in the veterinary context, okay? So I'd like to show you them. And fortunately, at least the first is very, very quick, okay? And we should be able to finish that in less than 45 minutes. Okay, so I'd like you to go create a new model, okay? And we are going to examine a case where we have system dynamics combined with agent-based modeling, not in the sense that system dynamics is within each agent, or even in the sense that system dynamics is an aggregate thing above the level of all the agents, which is another option. But rather, system dynamics and the agents exist at kind of lateral levels, in the sense that one is not within the other, but one feeds the other. Okay? So, ladies and gentlemen, I'd like to go create a two-stock model. Okay? So let's go create a model, and this is going to be called it's not hierarchical. Okay, lateral system dynamics ABM hybrid. Okay, and this is going to be, I'm going to go put this in my normal place. Okay, there we go. Okay, and the model time units here will be years. Okay. Okay, years, and we're going to say finish. Now, the idea behind this, as I say, is that we're going to have system dynamics and we're going to have agent-based modeling, but it's not going to be one within the other, but one sort of upstream of the other. But a given person, conceptually, will flow through both of them. Okay? One at a time. Okay, so what I'd like you to do is go, therefore, create an agent type called person. Okay? Now this person is going to have a representation. We'll use the little person icon, of which we have perhaps developed a certain fondness, for which we have developed a certain fondness. Okay? There's our person. Now, I could elaborate this into a more sophisticated example, but I want to communicate to you the essentials of what's going on. So And I want to move on to another type of hybrid modeling that I think offers a lot of veterinary relevance. So for this, we're just going to actually leave persons dynamics, state charts or stocks and flows or whatever. We're going to leave that out for now. We're just going to show how these people get created from a system dynamics model. So the idea here is that we're going to have, so system dynamics model, an aggregate system dynamics model often has stocks of people, and those people flow between the stocks, okay? So you have a compartmental model. Think about SIR model. People flow from S to I when they get infected, and then on to R, maybe when they recover, what have you. And what I'm going to ask you to imagine is, imagine if one of those flows of that signals start of a period of great interest, if that flow, instead of going into another stock, it actually creates agents. Agents who represent this population of particular interest. So the idea here is the system dynamics population is probably going to be most of the population, maybe 90% or 80% of the population. But when agents enter a state, maybe it's a state of being at risk or a state of developing prediabetes, maybe it's a state of developing some preliminary signs of chronic wasting disease, they actually get differentiated as agents, and then they can be followed in all their detail. Their social networks, their physical location and GIS space, their history over time, interventions upon them, all that can be simulated in great detail. So maybe it's someone gets infected with HPV and they become an agent, and from then on their progression to risks of cancer and to treatments and screening, all of that's followed at an agent level. So here, system dynamics has a coarse-grained representation of most of the population, and then they become individuated as agents when they reach a certain part of the risk continuum. Okay? So this is the idea. So, ladies and gentlemen, I'd like to go to Maine now. Let's go down Maine, and I'd like to draw a set of stocks and flows. Okay. So if we could, I'd like to now go represent. So we're going to go to the palette, and we're going to represent a system dynamics, and we're going to have susceptible individuals. And then we are going to have a flow here, which is going to represent an individual who is, and actually I think what I'll do is to add a bit of texture to it, I'll make an exposed individuals. Exposed, these are people undergoing latency, they're in their latent period. Exposed. And then we're going to have a flow which is going to take us in a different direction. Okay? And I am going to go and place in this stock here, this stock right here, it's going to be infectives to be created as agents. Okay? Okay? Are we okay with that? Okay. Okay, so let's do this. This flow from susceptible to exposed will be called infection. The flow from exposed to infective will be called completing latency. Okay, and what we're going to do is we're going to layer on this the trappings of classic system dynamics compartmental formulation. So we're going to have a contact rate, okay, and this contact rate is going to be a rate, okay, and it's going to be a rate per month of contacts, and by default it will be a value of 10, okay. We're going to have a parameter that's going to be beta, and in a compartmental modeling sense, which is transmission probability per discordant contact, although I won't write that out. And we're going to have a dynamic variable, ladies and gentlemen, which is going to be total population, okay? And then a dynamic variable which is going to be fractional prevalence, okay? Okay? Okay, so, ladies and gentlemen, what we're going to do is now put into place a force of infection. So there's going to be a variable here called force of infection. Now, for some of you, these may be meaningful terms. These are, you know, from theory of mathematical epidemiology. For others, maybe it's new to you. But I'll give you the formulas for these. These are classic sort of formulations. So we're going to have, going to total population, we're going to have susceptible, susceptible, exposed, infectives to be created as agents, and we're going to actually have one more term before the day is out. For fractional prevalence, we're going to have depend on total population plus the, okay, and I should probably, I'm going to have a dynamic variable called infectives, okay? And I'm sorry, total population will depend on infectives. This will be the total count of infectives. That in turn will be dependent on infectives to be created. So total population depends on infectives, exposed, and susceptible, okay? And then it will further depend on, we'll assume that people who become, well, we'll leave it like that. People maintain infection once infected. Yeah.
The arrows that are going to the parameters?
Yep.
Are those not links? What are those?
Those are links.
Any logic doesn't like that.
Okay, that's interesting.
That's because you're using parameters.
Yeah, these are
dynamic variables. Yeah, so parameters don't depend on another thing. They're inputs, and so your dynamic variables depend.
Yeah.
So your links can start there, but
yeah. Okay. Okay. So, ladies and gentlemen, this is what we're going to have. We're just about done with this. Itching this up. There we go. And this is just standard formulation using system dynamics of a stock and flow for infection. Okay, so I'm going to give you some formulas. Oh, we need one more parameter, which is duration. It's going to be latent period, mean latent period. There we go. Okay, mean latent period.
Doesn't fractional prevalence also have exposed?
Indeed. No, it's effective. So
Infectives?
infectives, yeah. So this will need a link over to this guy. Yeah.
That's infectives.
That's infectives, yeah. Okay. This is mean latent period. So I'm trying to show, this is like a classic formulation of a, come on, get over there, of a stock and flow infection model, but I'm trying to show where the agents will come in here in a slightly more articulated example than I already had planned. Okay, so here we are. So this is the basic connectivity. Actually, yes.
Probably need from the stock.
And sorry?
From the stock to the flow.
Yeah, I will. That's true. Yeah. Yeah. When we get to those. So here and here. There we go. Yeah. Good. Okay. Can I start to give you formulas for these? Okay. Okay. Yeah. Would you like me to make it?
So, yeah.
I'll make it larger.
Do we want to walk through the logic a little bit? Or no?
Well, I was going to do that with the formulas, but the basic idea is the total population is the sum of susceptibles, exposed, and infectives. The fractional prevalence is just going to be the total the effectives divided by the total population. There's going to be a first order delay associated with completing latency, so exposed divided by mean latent period. And the force of infection, the probability per unit time a given susceptible will get infected, shapes the number that are infected. And it's computed as the contact rate times the fractional prevalence times the transmission probability. And that force of infection is a hazard rate. It's a chance per unit time someone will get infected. And so the formula for infection is just susceptible times that. But we'll come and define that. So this is the classic mathematical epidemiology with compartmental models. This is kind of the bread and butter there of how they build the model. And again, the links indicate dependencies. So we're going to go and put in formulas for each of these guys right now based on the links. Are we okay? Okay, do you want me to hold off for another bit? Okay, so now we're going to put in the formulas for these guys. The good news is that the stocks are just going to have fixed constants for their initial values. Susceptible is going to have 999 people. Exposed is going to have 0, and infectives to be created is going to have 0 initially. Those are all the initial values. Okay, now we're going to go through, ladies and gentlemen, each of the parameters, and I'll tell you a value to use, and then we're going to go through the formulas. So for the transmission probability, I'd like to use a default value of 0.04, 0.04, For the contact rate, I had mentioned 10 per month. The transmission probability is the chance per discordant contact. So for a given contact between a susceptible and infective, what's the chance the infection will be transmitted? Mean latent period, ladies and gentlemen, I'd like to make it 10 days. So this will be of type time, it'll be in days, and it will be 10 days. Are we okay? Okay. Now we're going to fill in some gaps. So, ladies and gentlemen, for force of infection, going from the left to the right, actually, let's go from infection, this flow. Are you ready for the infection flow? Are you ready for that? It'll be susceptible. You might want to look what's pointing at it. The two things that are pointing at it will give you a hint as to what this is going to be. Oops. One, it's going to be susceptible times, remember to do control space, force of infection. That's what the formula is for infection. Are we okay with that? We okay?
Yep.
Anyone want me to wait a bit? Okay. Now let's go to force of infection. And for this, the force of infection, this is probably the most critical formula and subtle formula of the whole thing. It's contact rate. So suppose I have contact with 100 people per day, of anyone, and of those people, suppose fractional prevalence are infected. So I have contact with 100 people per month, 50% are infected. So on average, I have contact with 100 times 0.5, or 50 people per month I have contact with. And then for each of those people, of those infectious people with whom I have contact, remember, I'm 100 total people, of them 50% are infected, so I have a contact with 50 per month infected people, and for each of those people, I have transmission probability of becoming infected. And this is the approximation that's the standard approximation in a compartmental model. So contact rate times fractional prevalence times transmission probability gives force of infection, gives this chance per unit time someone will be infected. There it is right there. You should be able to auto-complete this. Are we okay with that? Okay. Okay. Next. For fractional prevalence, we're going to have infectives divided by total population. It's the number of infectives divided by the total population. That's what fractional prevalence is. Total population, so again, fractional prevalence is infectives divided by total population. And in case anyone missed it, force of infection is contact rate times fractional prevalence times transmission probability. Okay, ladies and gentlemen, total population is going to be susceptibles plus exposed plus infectives. There we are. Total population. Are we okay with that? Total population. Okay. Are we okay? Okay. And now for this guy here, for completing latency, it's just expose divided by mean latent period. That's a first order delay. And we've seen it before, several things of this type. Mean latent period. Oops. Latent period. That's it. Okay. Now, that's all we're going to fill right now. And we're most of the way done with this. So, ladies and gentlemen, this is what I'd like you to do. This may look like a system dynamics model, but it's not. It is, but it's also going to be an agent-based model. So, to show this, I'd like you to go and create a population of agents in main in the standard way. Just drag person in, make it population. So drag person in to become a population. And it's a population of agents, initial size is 0. Are we okay? Okay, now, having done that, ladies and gentlemen, I'd like to go back to this dynamic variable we didn't complete, infectives. A dynamic variable is a variable that's going to be updated on an ongoing basis as things change in which it depends. So for infectives, what we're going to want for this is a value that is the sum of two things, okay? And one of these we need to stick in here, a link. This one here, this bottom one. Hey, come on, here we go. There we go. There we go. So infectives itself is going to be a sum of infectives to be created as agents plus, ladies and gentlemen, population you know what? I'm going to call this population, just to be clear, I'm going to call it infectious population. Forgive me, I just want to be clear about it. Infectious population. So it's less confusing to people. Infectious population. Okay? And infectives is going to be the sum of infectives to be created as agents and infectious population dot size. Are we okay with that? Okay, now the magic time comes. The time where these two types of modeling join together. Everything else has been more or less standard one or the other within this model. Now it's the time for the interaction. And how this happens may surprise you. Go over to the agent palette and drag in an event. And this event will be called create agent trigger. I'm going to call it create agent trigger event. So that if I look at its name, I know what it is. It's an event. Okay. Okay. Now, this event is also going to be a different sort than you've seen. The trigger type is not timeout, nor is it a rate. It's a condition. Ladies and gentlemen, this event will fire when infectives to be created is greater than or equal to 1.0.
Why does it have false in there originally?
It's just, if you don't specify, it never fires.
Okay.
Yeah. So it should be infectives to be created greater than or equal to 1.0. Okay? So it's only going to run if there's an agent to be created, at least one full agent to be created. Okay. Are we ready? Now there's a bit of mechanism. Okay. Here we go, ladies and gentlemen. In the action, remember, events exist to perform actions when they're triggered. Their modus operandi is they're going to perform an action when they're triggered. So what's the action? That's where the action's at. Ready? Are you ready? Okay. Int count agents to be created equals, I'll put this up on the big screen, int of diabetics, infectives to create as agents. Infectives to be created as agents, okay? There we go. And now, for for int I equals 0, we're going to loop this many times, count agents to be created. We're going to loop that many times, okay? And for each of those times, we're going to add somebody to the infectious population. Who are we going to add? A what? Who is this thing we're adding? What is it we're adding here? Anyone? It's a what? Yes, it's a person. It's an agent. Okay? So I'm going to then remove the number of agents we've created from the queue to be created. So there's some number of agents waiting to be created. I create that many and say, okay, I've created them, so we don't need to think we're waiting to create them anymore. There's some people left over. Maybe there's 0.3 agents left to create, but those will have to wait till later when the total count to be created is greater than is greater than 1, and then I restart the event. So this is the action. I'll go put this on the big screen, and you can see it. Here we go. That's what it is. Okay, so what's happening here? There's a stock, ladies and gentlemen, a stock of agents to be created. That's what this stock is here. This stock right down here. These are agents awaiting creation because they've reached a point in their risk continuum where they're worth following as individuals. Because maybe we care about their contact networks, maybe it's because we care about their individual histories and biographies, maybe it's because we care about their heterogeneity, maybe it's because we care about where they live, about their decision making. This is the stock of people waiting to be created as agents. We get here a count of them to create, an integer count. So maybe there's 3.4 waiting to be created. Count agents to be created is 3. It's the integer part of that. We then iterate up 3 times and create 3 full agents into our population. the count of infectious people to be created has been 3.4, but we've created 3, so we deduct that 3 from it. So now there's 0.4 agents to be created at some later point once it gets above 1. And then we reset this event so it'll fire again later once the stalk again reaches 1. So this stalk here, this is just a transitionary stalk when they're awaiting creation as agents. The idea is we have a big population. Maybe these infectives are 0.1% of the population. 99.9% of the population perhaps is over here, and we don't want to represent all the details of their histories, their background, where they live, their contact patterns. We don't need all that detail perhaps for this part of the population. Maybe that understanding is just not there. Maybe we want to focus in on this sub-piece of the population. In another context, these might be those who have prediabetes and beyond, or these might be individuals who have had some, exposure to a certain environmental hazard. Small segment of the population, and we create that segment as agents. The rest are represented in a stock and flow model, and they flow down to become agents at a certain point in their risk continuum. So, ladies and gentlemen.
Please go back there.
Yeah.
Just missed one part of that.
Yeah.
So how old is the one that you'd uploaded to the site?
So that was the finish of the last one, and I can upload this right now.
Okay, if you could, that'd be great.
Yeah, you bet. It compiles okay, and let me take a sneak peek to just make sure it's working okay. Okay. Oops. Okay. Okay. So give me just a second here, and of course. Sorry, folks. One other thing. The number exposed here, that should start as 1, not as 0. Sorry about that. 1. This should start as 1. Initial value, not as 0. And I'll get that to you in just a sec. I just want to make sure it's hunky-dory. Okay, good. Okay, there is one other thing I'm going to have to ask you folks to do, and it's a familiar thing. We want the agents that come in to be located at random X and Y locations. Where do we go for that? In the population, we want to have them be located between an X location between 0 and space width, and Y location between 0, ladies and gentlemen, and space height. This is for the population. This is old hat stuff we've done for many agent populations, right? It's just the standard stuff to situate people at random locations in the population. Okay, let me just make sure that this is going okay. Okay, yep, here we are. Oh, what a thing of beauty. Okay, there we go. Okay, I'm going to upload this, and I'll call it version 1 in case we make any changes, V1. And let me tell you when that's on there. It will be on there in about 30 seconds, okay? Okay, it is done.
Can you just go back to that?
Yep, lateral SD ABM hybrid 1. Sorry?
Just the event.
The event, yeah. So the code like this?
Yep.
Yeah. So again, maybe we have 4.2 agents in this stock here, infectives to be created. 4.2 have flowed down here and are waiting to be created. We're going to say, 4 of them are ready to be created. They're complete, 4 complete people. We're going to loop through and create 4 such people. And then, ladies and gentlemen, we're going to take 4.2, the number awaiting creation, and subtract off the 4 we've created to just leave it with 0.2, and then we're going to get the event ready to fire again the next time there's a quorum to be created. Quorum is if there's one person to be created, at least one complete person to be created. And I would highlight this, if I may. For this event, this should be a condition event. Mark my words, a condition event. And this is the condition. Right there, that's the condition. It's a condition event. This event fires if this condition is true, if there's quorum. If there's at least one full agent waiting to be created, it'll create the missing agent. Are we okay with that?
Can you go back to the systems dynamic?
Sure. Yep. Okay, and what would you like me to look at there, or just the overall structure?
Still connected.
Okay. Yeah. So I can zoom in if you'd like.
Yeah, that'd be great. Thanks.
Okay. Kurt?
Yeah.
Oh, okay. Maybe you could.
Yeah, you can go ahead if you need to.
Well.
No, I was just gonna get my tea. That can wait. Is it erroring you?
Yeah, couple.
Oh, right. It's probably 1 and 2.
Yeah, weird. A lot of them are just, it's expect one thing and then come out there.
Yeah, so this one here says that it's using this thing called infections. And you don't have something called infections.
You need that.
Yeah. Autocomplete is your friend.
Okay. Can I help anyone else?
Let's try that.
Sean?
I'm just walking through, seeing if I can actually follow.
Or Nick?
It's a function.
Or Tiffany? Can I help at all?
Small problems, I think.
2
I
brackets.
think I'm okay.
Okay.
The first one is the universe.
Nick, would you like me to take a look?
That's all right.
So
That's the speed process.
No,
It's just what?
So,
There's something wrong here.
Okay.
remember how in some of those functions we have to specify an input parameter?
Right.
So that normally goes inside this pair of brackets that are there.
Got
So
it.
every function needs a pair of brackets, and that's where you put your input. But if there is no input, you just
Oh,
use
yeah,
empty
yeah, those
instead.
things.
Okay.
Oh, but you
Yeah,
actually,
both.
you need
Sorry.
parentheses, because these are calls to space
And you're
with.
gonna say 0. You gotta put
That's,
something.
otherwise it'll be an unhappy camper.
Okay, cool.
Yeah, oh.
There.
Yeah.
It's pretty slow.
Let's get a-
If you autocomplete that, it'll automatically.
Yeah, okay,
Oh,
I'll make,
right.
see if it builds in.
So space wait, autocomplete, wait.
Okay, okay, 2 errors.
Yeah.
Okay, so go count agents to be created, go up, okay, so, this is just misspelled, count
Wait.
GT.
yeah.
HT.
This is spelled correctly, but
That was
it
misspelled.
was
I think it
misspelled
was
earlier.
GH
When you declared it.
instead of
So I would
GH.
copy this, just Control C,
Do I want
and
this?
put it over.
Oh, right. No,
Oh,
wait.
Double click on that guy.
Autocomplete is your friend. Every single error you've seen has been because
no,
of that.
okay,
so
so
far.
double click on this guy.
So it doesn't know susceptible because
yeah.
it's not called susceptible.
Yeah, in fact, that's it. Okay, now try building it. Okay, okay. Can you see where?
Used but not expected.
Oh, you need a
Fractional
semicolon
prevalence.
after that.
Semicolon.
Okay. So
Yeah,
where's
before the, no,
After infection.
after.
Yeah.
So
That's
so
a T,
in force
yeah.
of infection, you're using fractional prevalence,
Okay.
but there's no arrow.
Cool,
going.
okay.
Okay,
Okay,
so
very
this
good.
is probably not.
No, it's fine. You just need to put an arrow from fractional
You just
prevalence
highlight
to force of infection.
So there can be an arrow connecting one, but if
The
don't include it
infected
in
to
the
be
actual
created
code,
You see
agents
here?
is good enough.
Oh, yeah, I see it there.
I'm sorry, so
No,
This
just-
infected.
But this,
Yeah.
this link here is going off.
would you like me to look at it?
That probably meant
The
to
box
go
you just,
there.
you had highlighted.
Yeah.
It's when over I want to answer your question about.
Yeah.
properties.
About this thing?
Yeah.
Yeah. So basically, what's happening is this is a new type of hybrid model where you have system dynamics and agent-based model coexisting, not with one strictly inside the other. So it's not, each agent has a system dynamics model inside of it. And it's not that there are a set of agents and they drive a flow and a system dynamics model above them. Rather, it's that people start life, most of the population is represented as system dynamics population, so maybe 90%, 80% of the population on whom we have less direct interest and are not of focal interest. They're represented using system dynamics in a coarse-grained way. So maybe it's people who are not at risk, maybe it's producers who don't heavily use antibiotics or what have you. But then there's a subset of the population that's of particular interest, of focal interest, where we might want to keep track of their history over time, have targeted interventions that take advantage of that history or characteristics of heterogeneity associated with them. Maybe we want to keep track of their spatial locations. Maybe we want to keep track of their networks or their individual decision making. In short, for those people, that subset, a small subset of the population, we might be interested in a much more detailed view that's amenable to agent-based modeling. And rather than just saying we're going to simulate the whole population with agent-based modeling, we have most of the population with system dynamics, and once people reach a certain point, say in the risk continuum or in the point of their development where they become part of focal interest, then they get turned into agents. Before that, they don't need to be represented as agents, and we can save time by not representing them as agents, both running time and time researching things. We'll just have a rough and ready model for them, and then it's only when they get caught or when they develop HPV infection or what have you that they become individuals as agents. They develop prediabetes, and therefore they're of particular concern for a diabetes model. So here, most of the population would be here, but once people become infectives, then we might turn them into agents. So if we run this model, ladies and gentlemen, what you will see is people starting in this population here, but over time, people will turn into agents because they've reached this point in the continuum. They've reached this point in their flow where they're worth representing as an agent. And by representing them as an agent, then we can take full advantage of agent-based modeling. Again, GIS position, representing personal decision-making, representing their connections, capturing their history over time. And so here, system dynamics model, characterizing most of the population, agent-based model, characterizing the population of greatest interest, and potentially, for some of our models, we've had people, after going through a period of interest, flow back into the system dynamics model. So that they don't have to stay agents forever. Maybe it's only when they present for care and when they're under a certain type of care process, but after they receive their, certain treatment protocol, they then become part of the general population. So this is another example of a hybrid population, upstream system dynamics, sometimes downstream as well, but agent-based modeling for the population of greatest interest. Okay? So that's a type of hybrid modeling that we've used to really good effect for some of our work, particularly with end-stage renal disease modeling, modeling diabetic end-stage renal disease, and we have a very detailed view for a subset of the population and a very coarse-grained view for the rest. Okay? So that's a type of hybrid modeling that you may find of interest because it's often lends an economy of representation. You don't need to research all sorts of individual level details on most of the population and can really put your efforts into that subpopulation. So that's one model I wanted to build with you. Okay? Any questions on that before we go on to a final model for the day, hybrid model of great utility for veterinary science? No? Okay. So I'm going to close this. I think it's the same one I posted just 5 minutes ago, but I will, just in case, post it up there again. And we will go and prepare for the next model. Now is a good time for a bathroom break. For sure.
Since
They all